In section 3 of chapter 9, we're going to take a closer look at margin of error and paired t procedures. So for margin of error, when it comes for means, there are two different margin of errors you could have based on your confidence intervals. One is if you are given your population standard deviation, and one is used if we are given the sample standard deviation. So if we're given population standard deviation, we have that our margin of error is our z critical value times the standard deviation over the square root of n. And if we're given our sample standard deviation, the margin of error is the t critical value times the sample standard deviation over the square root of n. Same basic formula. You're doing your test your critical value times the standard deviation of the square root of n. It's just what type of critical value you're using and which standard deviations are you using. So it's a few problems with margin of error for means. One, we haven't gathered the data yet, so you don't know the sample standard deviation. All right, because our t critical value depends on the sample size we choose, because it involves degrees of freedom. So the problem is, if we want a set sample size or margin of error before doing a study, this is a problem. Okay, so this is based on if we use our margin of error formula for a sample. Okay, so the alternative and the only thing we can do is come up for a reasonable estimate for the population standard deviation from a similar study that was done in the past. So that's where the other formula is going to come in. So by pretending that we have a known standard deviation, we can use the one sample z interval for mean. So we're going to end up using the margin of error formula for a z critical value, which uses population standard deviation over the square root of n. That way we don't have to worry about a t critical value and a sample standard deviation, which is all based on n anyway. So therefore, with using this formula, we can set a margin of error to be less than or equal to a certain value, and we can solve for n. So in our example, we want to estimate the mean cholesterol level of a particular variety of monkey that is often used in laboratory experiments. They would like their estimate to be within 1 milligram per deciliter of the true value of our mean at a 95% confidence level. A previous study involving this variety of monkeys suggests that the standard deviation of cholesterol level is about 5 milligrams per deciliter. Obtaining monkeys for research is time-consuming, expensive, and controversial. What is the minimum number of monkeys the researchers will need to get a satisfactory estimate? So our margin of error, if we search through the problem, is 1 milligram per deciliter. We're going to have 1. We are using a z critical value, which involves using our 95% confidence level. So we would do INV norm. Sorry, not INV norm. Yeah, we'd use INV norm to solve for our z critical value, which ends up being 1.96. We have our standard deviation from the problem, which they say is 5 milligrams per deciliter. And we're going to solve for n. So setting up our formula, we have 1 equals 1.96 times our standard deviation 5 over the square root of n. So this formula is a little bit easier to solve for So what I'm going to do over here is I'm actually going to rewrite a formula that is based off solving for sample size. So you have kind of a generalized one that you can use. So what we end up getting is that the square root of n equals the z critical value times the standard deviation over our margin of error, because we would multiply by the square root of n and then divide by the margin of error. And then to get rid of the square root, we would square both sides. So we end up with the formula n equals our z critical value times our standard deviation all over the margin of error squared. So we can use that formula instead of having to solve for n. So reordering, we'll have n equals 1.96 times my standard deviation 5 all over 1 squared. So 1.96 times 5 divided by 1 is still 9.8, and then we square it and we get 96.04. But just like with proportions, we always round up. So 97 monkeys. So always round up. So it's definitely a nicer formula than proportions. We still have to square to solve for n, but it's a little bit easier of a formula to complete. The last thing we're going to talk about is matched pair data. So comparative studies are more convincing than single sample investigations, because you're comparing it to previous data showing that it's a better or worse thing depending on what side you're on. So for that reason, one sample inference is less common than comparative inference. So study designs that involve making 2 observations on the same individual or 1 observation on each of 2 similar individuals result in paired data. So this is kind of a review from when we were talking about studies first semester. We talked about matched pair. So when paired data result from measuring the same quantitative variable twice, we can make comparisons by analyzing the differences in each pair. If the conditions for inference are met, we can use a one sample t procedure to perform inference about the mean difference, which is mu sub d. And these methods are called matched pair procedures. Okay, so let's take a look at an example. So for their second semester project in AP Statistics, Nick and Kai decided to investigate which line was faster in the supermarket, the express lane or the regular lane. To collect their data, they randomly selected 15 times during a week, went to the same store, and bought the same item. However, one of them used the express lane and the other the regular lane. To decide which lane each one of them would use, they flipped a coin. If it was heads, Nick's would use the express lane, and if it was tails, Kai would use the express lane. They entered their randomly assigned lanes at the same time, and each recorded the time in seconds it took them to complete the transaction. Is there a significant difference in checkout times? So we're basically figuring out, is the time in the express lane quicker than the time in the regular lane? So by pairing data here, we are controlling the store busyness, the items purchased, etc. So when we're looking at what our mu sub d represents, it's the average time difference between express and regular. Because it doesn't state an alpha, we know to automatically use 0.05. So for our null hypothesis, the difference should be 0. There shouldn't be a difference in which lane you choose. The alternative, so they're trying to test if there's a significant difference in checkout time. So they're looking to see if the mean difference is not 0. So it would mean that one of them is faster than the other. So the way that we're going to enter this in our calculator, we're going to go stat and edit, and we're going to use 3 lists. So list 1 is going to represent the time in the express lane, and list 2 is going to represent the time in our regular lane. Once you're done putting your times in list 1 and list 2, what you then want to go over is to list 3. And in the header part of list 3, you want to do L2 minus L1. And the way you do that is you hit second 2 and then minus second 1. And then you want to hit enter. And this gives us the differences in time. Between the lanes. Okay, and this is the list that we're going to use to calculate our mean and our standard deviation. So now when we go to stat and we go to calc and we do one variable stats, we want to make sure that list that it's pulling from is list 3. I actually wrote that wrong. So because we're finding the difference between express and regular, at the top of list 3, you should do L1 minus L2. And then you'll go to stat, calc, one variable stats, and then you'll use list 3. So the mean difference between the lane times is going to be negative 42.67, and our standard deviation and because it is a sample, we want to use the SX is 84.02. And it is okay for the mean here to be negative even though it's time, because that's indicating that the express lane is faster than the regular lane. If it was positive, that would indicate that the regular lane was quicker than the express lane. Okay, so now we're going to check our conditions. So for random, the 2 kids did randomly select the times they were going to go and the lanes they were assigned to. So random time and lanes. Independent. So our sample size is 15, so that's less than or equal to 10% of, in this case, all hours and lanes open. So we are going to assume that one lane doesn't affect the other lane. We're going to assume that if you choose one regular lane over the other, that does not change the likelihood that you'll get through that lane faster. So we'll assume that all of the employees work at the same rate in the regular lane. And then lastly, we have normal. Now, because our sample size is only 15, we will want to check our graph. And we want to check the graph for the box plot. For list 3, not list 1 or list 2. And it is roughly symmetric. You could also do a bar graph. I know I've talked about on all of these, like doing a box plot, but you can actually do a bar graph as well. And a bar graph actually might work a little bit better in this instance. And it might be a little bit easier to tell if a distribution is normal. So if we look at the graph, it is approximately normal. So now we can go ahead and calculate our t statistic. So we're our sample, negative 42.67 minus the null hypothesis, which is 0, over our standard deviation, 84.02, over the square root of n, which is 15. Which gives us negative 1.97. So now to find our p-value, we are going to go to TCDF. Our lower bound will be the negative 9s, our upper bound will be negative 1.97, and our degrees of freedom are 14. And we get 0.0345. Now the important thing to remember here that we do have an alternative hypothesis of does not equal, so we do need to multiply this value by 2. So our p-value is actually 0.0689. So if we compare our p-value to alpha, which is 0.05, it is greater than alpha, which means we fail to reject the null hypothesis, which means there is not convincing evidence of a difference in checkout lane speeds. Please let me know if you have any questions over the margin of error solving for n or the matched pair significance test.